video number 52 in my series on arithmetic, algebra, and graphing, part 11 of a subseries that includes an emphasis on spreadsheet usage. In the last video, we looked at an example where y was inversely proportional to x. We wanted to answer some questions that you see. What was, if you suppose that y is 2 when x is 4, what is y when x is 8, when x is 16? And what value of x will make y equal to 0.125. This is the kind of function you want to set up, and these questions are all easy to answer just using algebra without actually making a graph and without actually making a table of values. But I think it's nice to make a graph and a table of values to especially see the pattern with the graph, that it's a decreasing function that is also called concave up because it's decreasing, so it's always going down. But the rate at which it goes down slows down over time as x increases, is what I really should say there. What's an application of this? Well, a basic application would be, for example, if 8 is how far you have to travel to go to work, and x is your speed, then y is your time. For example, if this is 8 miles and this is 0.1 miles per hour, then it'll take you 80 hours to get to work. Now, 0.1 miles per hour is like a snail's pace. At 1 mile an hour, it'll take you 8 hours to get to work, to go those 8 miles. On the other hand, if you go 55 miles an hour, it'll take you 0.145 hours. What will that be? I'll just do it quick here. My calculator, about 8.7 minutes is what that turns out to be. Because in this formula that was in this cell right here, because I used a $sign, B7, one nice feature here is if I feel like changing the constant of proportionality to, say, 10 instead of 8, everything automatically gets updated. Watch it here. Everything gets updated. The y values got updated, and the x, well, the graph got updated too. I don't know if you noticed that or not. Let me look at a wider view here so we see that better. If I change the constant back to 8, watch the graph. I think what will happen is the scale will change and the graph will look basically the same with a different scale. Yep, there we go, the scale changed. So it is a different graph, it is a different function, though it has basically the same shape. And it has similar properties. If x doubles, then y will get cut in half no matter whether the constant is 8 or 10 or whatever. For example, if the constant is 20 and x doubles from 1 to 2, you can see y gets cut in half from 20 down to 10. That'll happen no matter what the constant is, though the particular values of y change. If we go back to 8, y goes down from 8 to 4 as x goes from 1 to 2. Alright, another example. This is an example I did in a video a while ago. Suppose you deposit $1,000 into a certificate of deposit, a CD, which earns 2% interest per year. How much will be in the CD after 10 years, after 20 years, and when will you have $2,000 in the certificate of deposit? I'm also wondering how our answers change if the interest rate is 4% per year or 8% per year. So let's make a spot where we can put the interest rate. We can put it as a percentage as long as we use the percent key on Excel, I believe. But let's type it in as a decimal. 0.02 is what we're going to start off with. X is going to be the number of years. And since my answer to the last question could be, 0.5 or 0.1 years, maybe I do want to do, well, let's just do it to the nearest 0.5. You can do however much you want here. I'll make this go up by 0.5 half a year every time. Drag this on down a ways. Okay, that's probably good enough. Then y is going to be how much money. As far as the formula goes, we've talked about this before, you do 1,000 times 1.02 raised to the x power. So now x is in the exponent. This is called an exponential function. And that 1.02 I probably should type in like this. Watch this. I got the equals 1,000 times 1 plus B7 with $signs. is probably the best way to represent the 1.02 if I want to allow myself to make changes. I'm raising it to the x power, which is in cell B10. Don't use dollar signs there. Look at that. Compare it with the formula. Do you believe you could do that on your own? Make sure you come to the point where you believe you could type that in on your own and be correct. Let's check that it works by going up to 1 year. Yes, our money increased to $1,020. It increased by 2% in 1 year. It increased by 2% in the second year also, but that's more money, $20.40 as opposed to $20. That's because $20.40 is 2% of 1,020, whereas 20 is 2% of 1,000. This function will have a graph that is concave up as well as increasing. There are the numbers. We can answer the questions real quick. How much after 10 years? How much after 20 years? $1,218.99 after 10 years. $1,485.95 after 20 years. And when does it reach 2,000? Well, remember, this is approximately 35 years. That's real close to 2,000. Pretty much 35 years is the answer to the last question. Let's graph it. Going out to the 35 at least here. Charts. Already on scatter plot. There we go. Here's the graph. It's increasing. Your money goes up over time, and it's also concave up. It looks like part of a bowl or part of a smile if you prefer. How do the answers change if we change the interest rate, for example, to 4%? 10 years before, we were up to about a little over 1,200. After 14 or 20 years, we were up to a little over, well, almost 1,500. If I change the interest rate, if I double it to 4%, it also took 35 years to get to 2,000. What happens to the answers? Well, watch the graph will change when I enter this. It's a little bit more concave up. It's increasing faster. After 10 years, it's almost up to 1,500. After 20 years, it's over 2,000. Takes a little less than 18 years to get to 2,000. I'll change it to 8% now. Look at that, the graph became even more concave up, increases faster over here. After 10 years, you're already over 2,000. After 20 years, you're up on getting close to 5,000. And it reaches 2,000, about 9 years into it. Wow, those are pretty big changes. This is a nonlinear function as well, increasing in concave up, and small changes in the interest rate can greatly affect the results. Let's go even more extreme. What if you had 20% interest? Wow, 0.2. You get to $2,000 in less than 4 years. After 10 years, you're up to $6,200. After 20 years, you're up to $38,000. Wow, 20% interest rate. That's real great, but unfortunately, that's hard to get. So while compound interest is real good and increases, your money amount increases real fast if you have a high interest rate, it is tough to get interest rates that high, especially these days.